Okay, so this is the feedback for the Evolution of the Living Earth exam. So this is the last part, Part D, which is the section of the course on biogeochemical cycles. So if we head into the exam, probably we're going to look at, I guess, question 7 first. But just to point out, so there are 2 questions in this section 1. First on CO2 in the atmosphere and the variability between years, and the second question, or last question on the exam, is about the sulfur cycle, and that will be discussed in another video. But looking at the overall marks for this part of the course, question D and question D7 and D8. So these are the questions on biochemical cycles. Just like with most of the parts of the exam, some people did very well on the course, and on these questions in particular, people getting first, some people getting kind of very, very high marks. But there's a large tail of people getting quite low marks, below the 40% pass mark. So hopefully, just with the other videos, this will just give you some pointers to what we were looking for and why you didn't, get that. So this first question, D7, is going to be about atmospheric CO2. This is a picture of the Mauna Loa Astronomical Observatory, which is where some of the measurements for this question were taken from. So let's look at the question in its entirety, or in parts for starters. So it was all about this figure over on the right here. And there was a big bit of description. We'll just go through what that means. So we have over here. So the solid line. So that's this line here. That's the atmospheric CO2 measured at Mauna Loa. So this is not the global average. It's just measured at this one point in the globe in the northern hemisphere. And then we have pH measurements, which are measured near by the islands of Hawaii in the ocean, and these white circles here, and I've put a kind of a smoothed running average through those pH data. I've also described what the age scale across the bottom here. So we have years, 2005, 6, 7, 8, and the intersections, the tick marks on the axis here actually represent the start of this year. So this period here is all 2007, 2008. So just to kind of help out, I've put some color bars across this diagram to show where summer time is approximately and where winter time is. So you can see January, the first line, kind of somewhere in the middle of winter. Okay, so we've got kind of December, January, February, kind of like in winter, and then summertime is the summery time. Okay, so that's set up what this graph is showing. Let's head on now and look at the actual parts of the questions. So the first question, part A, is explain the processes that are responsible for the annual cycle in the CO2 data. So this is a question that just looks at the solid black line. It doesn't really taking any notice of the pH data. We can kind of think about this as rewriting the question in a different way. That's perhaps a little bit more prescriptive as to why CO2 goes up during the winters and down during the summers. So that's, I guess, the first observation one could make of the CO2 data. So that could form part of your answer to 7a. CO2 goes up in winter, down in summer. That's not what the question is asking, but it could form part of your answer. So in terms of adding more information, just a more detailed description, other than there is some variability. You could define what that is. So looking into the reasons for that, this is kind of a screen grab from one of the videos that I showed in the lectures, is that we have kind of large changes. The color scale on this plot is the CO2 concentration in a climate model assimilating some data. That we have basically large annual changes in the CO2 concentration in the atmosphere. This is a measurement from 2006 in February, I guess that's the second month of the year, February, and looking forward on to the next one. And this is August. That's the 8th month, I think. Anyway, and you can see that toward the end of summer, we have much lower CO2 concentrations, particularly in the northern hemisphere. They've gone down quite a lot. So the processes responsible for this are, of course, photosynthesis and respiration. So when we have lots of photosynthesis going on in a particular part or hemisphere of the planet, that removes CO2 from the atmosphere. When we have more respiration than we have photosynthesis, that adds CO2 to the atmosphere. So the idea here is that in winter, we head on to here, winter we have more respiration than photosynthesis, because photosynthesis requires light, which is absent in high latitudes in winter. If you live in Scotland, you'll know that there's not a lot of light, so there's less photosynthesis, but respiration happens the year round. Whereas in summer we'll have more photosynthesis, and that'll be drawing down those CO2 concentrations. So the kinds of things that your answer could include is a mention of photosynthesis and respiration and why they're different in different seasons, in different hemispheres, whether it's responsible for light or warmer, and also including some of the formulas for photosynthesis and respiration. Just this little X here is to point out that there is no back reaction. These are two separate processes, although the reactions are summarized in the same way here. Okay, so that's the first part. The next part is looking on why is the rate of change of CO2 within the yearly cycle large compared to the long-term trend. So just to explain what that means as a question, we can just have a look at the long-term trend. So the rate of change of the long-term trend is basically just the slope of this line. Okay, so the long-term trend is gradual increase in CO2 concentration year on year. But we also have superimposed on that this annual cycle, and that has steeper rates of change. So we can see basically the question is asking, why is the slope of line within the year much higher than the long-term trend? Okay. To address this, we need to think about what are the reasons for the annual cycle, which we answered in the previous question. So these are the fluxes between the atmosphere and the biosphere that are photosynthesis and respiration. And what are the processes that are responsible for the long-term trend? So I guess that we could rewrite that. I forgot that it's in the presentation. So we need to know what is causing this long-term trend, to say something about why the rate is slow compared to the rates from photosynthesis and respiration, okay, which we already know about. So here's another figure from the lectures, which is from the IPCC Climate 5th Assessment Report. And you can't quite see the numbers on this, so I'll just give it some bigness. Here we go. So we can see that we've got the fluxes into and out of the atmosphere from various different reservoirs here. So if we look at the black line, so these are the natural fluxes. We've got huge amounts of carbon coming from the biosphere out into from the biosphere out into the atmosphere through respiration, and a huge flux from the atmosphere to the biosphere through photosynthesis. Similarly, large fluxes between the atmosphere and the ocean. These are due to air-sea gas exchange, due to kind of Henry's law. Someone is dragging some very loud thing outside my office, which is extremely annoying. But what you can see here is that these fluxes, although they're large, they're roughly in balance every year. So what gets taken out of the biosphere by respiration is put back into the biosphere roughly by photosynthesis every year. So on a seasonal timescale, these fluxes are not in balance. Okay, and because they're very large, if you have a significant imbalance with them, that will lead to a very large rate of change in the atmospheric content. So that explains why these slopes are so large. And if we look at the fluxes that are responsible for the long-term trend, so these are these additional additions of carbon into the atmosphere from anthropogenic sources. So if we highlight this here, so fossil fuel burning, land use change, And these are kind of somewhat counteracted by this extra carbon actually being absorbed by the ocean or the biosphere. But we can see that these are not in balance. There is this net flux out into the atmosphere, which basically adds carbon to the Earth every year. But the overall flux is actually quite small. So we're looking at maybe 4 petagrams of carbon per year, every year increasing. So although the flux from these anthropogenic sources is I guess it is big. I mean, it is changing the atmospheric composition. It is very small compared to the annual fluxes through photosynthesis and respiration, which is why the slope of this red line is less than the slope of the seasonal cycle in CO2. Okay, so those are the things we were looking for in this answer. Some mentioned that the reason for the long-term trend, and also some assessment of the size of the long-term trend, or size of the fluxes that are causing the long-term trend, so the rates of carbon coming out from fossil fuel burning compared to the sizes of the fluxes from photosynthesis and respiration. These are very, very large fluxes. Okay, so the next part of the question was asking about what are the processes that could change the pH of the surface waters on timescale relative to the figure above. So really looking at the figure over here, we're basically asking, what is causing this variability in the pH of the ocean? And we've got 2 things to consider here. I mean, there's clearly some annual variability. So the smooth data looks like there's an angle cycle. There's a lot of scatter in the data, a lot of variability on short time scales, and there's also a long-term trend that's kind of gradual decline in pH over the 6 years or so of the graph. So there are processes that could change the pH of the ocean over longer time scales, so over maybe hundreds or thousands of years, but that's not what the question is asking. The question is really focusing in on processes that can happen on very short time scales. And can affect parts of the ocean, not necessarily the whole ocean. So let's have a look at what those could be. So we could rewrite our question before we kind of jump into answers. So we're really focusing in on these short-term changes, less than a few years. So we could start to think about what those processes might be. We could say, well, how does CO2 affect the water pH? And then what processes might affect the CO2 concentration? So rather than just focusing directly on the pH is controlled by carbon dioxide, which will hopefully would have formed part of your answer. But you could have taken this answer to kind of the next level by actually also addressing what are the things that affect CO2 in the water, which then affect dissolved CO2, in the water, which then affect pH. So there are a number of things we could have thought about here. And I guess another approach would be thinking about, actually, are there things that... So the graph kind of does imply that there is a link between CO2 in the atmosphere, okay, it's going up and down, up and down, up and down, and pH of the ocean. Now, we could think about, hopefully this kind of graph would have given you a clue to part of the answer to see that the atmospheric CO2 concentration might be involved in pH, because there's a graph of the 2 together. So hint, hint, there's going to be a link maybe with the rest of the questions. But there are potentially processes that happen that are not involved with atmospheric CO2 that might affect pH in the ocean as well. So we need to consider those in the round. So really, one of the really important things that an answer should have for this question is the link between carbon dioxide and ocean pH. So CO2 reacts with water. So if you have any CO2 dissolved in water, the more CO2 you have dissolved in water, the more hydrogen ions you'll have through this kind of series of chemical equilibria. And the more hydrogen ions you have, the lower the pH. So things like the definition of pH with respect to hydrogen ions and these kind of chemical equilibria would have been good things to have in an answer to this question. Additionally, what affects the CO2 concentration of the water? Well, if you increase the CO2 concentration of the atmosphere, that will cause more CO2 to dissolve in the water to maintain this concentration balance through Henry's law between the atmospheric partial pressure and the dissolved concentration of CO2. That relationship is often, well, is always temperature dependent. So you could have included, if you change the temperature, if you make it colder, you're going to dissolve more CO2 into the ocean. That will cause there to be more hydrogen ions, so will lower the pH. So there are lots of things that you could have added in to this kind of starter kind of relationship between a control on pH in the ocean and CO2. So we can then take this answer on a little bit further and think about what are the other processes, other than just exchange with the atmosphere, that could change CO2 dissolved in the surface ocean and therefore impact pH. So one of the processes that changes CO2 in the ocean is photosynthesis. So we have lots of organic matter production via photosynthesis that will remove CO2 from the dissolved phase in the ocean, which will then raise the pH. So if we have lots of primary productivity going on, this is kind of a schematic diagram of the ocean. So this is the ocean surface, this is the surface layer, and then you've got the deep ocean down here. If we have lots of primary productivity in this surface layer here, that means we're going to reduce the carbon dioxide concentration, because that's carbon dioxide being used for photosynthesis, and that will therefore raise the pH in this bit of the ocean. And that organic matter, when that sinks down to the deep ocean, that organic matter decays and will raise the carbon dioxide concentration in this deep water and therefore lower the pH of the deep water. Now, that deep water story is not really what the question was asking about. So you wouldn't need to put that into the answer, although it is relevant because ultimately that water will upwell at some point. And if you mix between surface water with a high pH and deep water with a low pH, if you mix those two together by upwelling, then you will change the pH of the surface ocean. So that again could be just another diagram which I forgot that I put in. Yeah, so this is the idea that lots of productivity in the surface ocean, lots of removal of CO2, that causes the carbon concentration or the CO2 concentration to go down, but raises the pH in the surface ocean and lowers the pH in the deep ocean. If you then mix these waters together by upwelling, if you upwell water from the deep Atlantic to the surface Atlantic, that would lower the pH of the surface water as well. Okay. So the last part of this question was really actually taking a little bit beyond just kind of knowledge of stuff from the lectures and asking you to think about the data. So in this case, it's not really a specific question about CO2 and pH. It's a question about what I guess variability in data actually means. So if we look now at the question, what does the scatter of the pH data tell us about the mechanisms that are responsible for the pH variability? Okay, so if we actually have a look at the pH data, you can see that the CO2 follows quite a smooth kind of continuing up and down curve, which you might remember from the practical that we did on CO2 and ocean pH. But in the pH data, there's quite a lot of variability. There's quite a big spread of data, even data seemingly collected on the same day. You see these 4 data points here, seemingly got almost the same day, but they've got a huge amount of variability. So the question asks, what does that tell us about the mechanisms that were responsible for the pH variability? Okay, so if we think about in the previous question, we basically came up with a effectively a list of lots of different possible ways that the ocean pH could change. Okay, so those were changes in atmospheric CO2 concentration, that changing the dissolved CO2 concentration, changes in primary productivity in the ocean, changes in upwelling, changes in temperature. Okay, all of these things could have impacted ocean pH in some way. So if we think about the first one of those, which was atmospheric CO2 concentration. So if atmospheric CO2 concentration is the only thing that is causing ocean pH to change, so that's if you have high CO2 concentration in the atmosphere, more will dissolve in the ocean. That will cause there to be more hydrogen ions and therefore a lower pH. So if we look at the data on the graph, we can see when we have a higher CO2 concentration in the atmosphere, oh, wrong mouse, higher CO2 concentration in the atmosphere here, we do have periods of lower pH, and that kind of fits. But if it was the only process that was happening, we would expect the pH data to follow in a smooth kind of opposite, okay, the CO2 data. And it doesn't do that. It has a lot more variability. It goes up and down, which implies that there must be some process that happens on a short time scale that can change the pH. And because that process, if that process is happening on a short time scale, it can't be just the change in atmospheric CO2, because the atmospheric CO2 does not change fast enough to represent the change in ocean pH on these really, really short time scales of maybe hours or at least days. We've got this huge variation in ocean pH happening on a very, very short time scale, whereas on the same time scale, CO2 is only changing by a small amount. So from a point of view of answering this question, what I was really looking for is you to give some idea that there must be another mechanism other than just atmospheric CO2. There must be something else. Now, you could have gone in and said which of the other mechanisms, whether it was, we could say, could it have been primary productivity? So we might expect primary productivity to change on timescales maybe shorter than this long, slow change in CO2, but maybe not have huge variations on a daily scale. So you might have a big spring bloom that kind of like kicks off lots of biological activity at the beginning of spring, but that's not what we really see in the pH data. Okay, so we don't see at the beginning of summer, spring, we don't see huge, well, we don't see, I guess that's, we don't see, here we go, we don't see huge changes in pH at this time here. We just don't see it. So it might not be that, but there are other possibilities. It could be changes in mixing with the deep ocean. If you suddenly have a big storm, that might bring up quite a lot of water that's got a very low pH that might cause variability in the pH without affecting atmospheric CO2 too much, because that's kind of more of a hemispheric kind of like well mixed signature. So that's what we're really looking for in this question. We're looking for, first of all, a statement that says the pH variability can't be solely caused by the smoothly varying atmospheric CO2. There must be other controls. Now, you could have also said other things, like it could be that the measurements are not very precise. There might be issues with kind of data quality or something like that. I know these are all sensible things to think of as well, but what we're really looking for is just assuming that the data are correct and there are reasons for them to vary. Okay, so that was the question 7. Hopefully you got a bit more of an idea of exactly what we're looking for, and some of the areas where you could have perhaps expanded on an answer, given more examples, particularly of the processes driving ocean pH. That was part of the question which was perhaps answered the least well. So I guess just hopefully this has helped. If it's not helped, if you still don't understand stuff, then you know where my office is. Unless you don't know where my office is, then you can find me on the internet somehow, somewhere. Righty-ho. Then look forward to other videos of the other questions, which are somewhere being posted somewhere. All right. Stopping recording.